In this IPv6 and 6LoWPAN webinar, a detailed overview of the 6LoWPAN adaptation layer will be given by me. And more specifically, among the defined 6LoWPAN mechanisms, we will see thoroughly together the header compression operation. So we'll start with the next slide. So here is the typical 60s protocol stack. So as previously mentioned, this third session is dedicated to the 6LoWPAN adaptation layer. Indeed, we are going to see how 6LoWPAN enables IPv6 packet transmissions over IEEE 802.15.4 networks at the MAC layer. So here's the outline of my talk. So I'm going to start first with an overview of the IPv6 addressing and IPv6 header format. So it is very important to make sure that you are aware what each field of the original IPv6 header means or represents. Then in the second section, we will have a quick look, an overview of the 6LoWPAN adaptation layer. Then in the third part of this presentation, we are going to see in detail the IPv6 header compression mechanism, field by field, bit by bit. And in the fourth section, I will give you two examples of IPv6 header compression based on 6LoWPAN. So we'll have link local multicast and global unicast IPv6 addresses. And I will conclude this webinar with the UDP header compression mechanism. So I will give you how, in addition to IPv6 header compression, the 6LoWPAN adaptation layer proposes to compress the UDP header as well. So we'll proceed with the first part. As I said before, diving deeper in 6LoWPAN, I will give a quick overview of IPv6 addressing. And as you might already know, an IPv6 address consists of two parts. So we have the 64-bit prefix and an additional 64 interface ID bits. The 64-bit prefix of an IPv6 can be considered like the subnet mask used in IPv4 addresses. So the prefix identifies the network in which the nodes or the routers are located. Then the 64 bits of the interface ID identifies the interface of a node in that specific network that the prefix was previously identified. As simple as that. Now there are different kinds of IPv6 addresses. And in fact, if we look at the prefix, an IPv6 address can be in one of the following cases. It can be a loopback, can be a unicast link local, can be a global unicast, multicast, anycast, etc. Now, when it comes to 6LoWPAN, an IPv6 address must be compressed. Indeed, regarding the prefix part, so the first 64 bits, the addresses within the 6LoWPAN typically contain a common prefix. Or they may support up to 16 shared contexts among the nodes. Or the nodes typically target one or few central nodes that are called the root nodes. So this already reduces essentially the use of the different IPv6 addresses. Now, on the other hand, the interface ID is typically derived from the layer 2 MAC addresses, and therefore it can be elided. So no need to transmit the 64 bits from the source to the destination, both for the source and the destination IPv6 addresses. Now we are going to see the IPv6 header format. So here we have the typical IPv6 header format, which consists of 40 bytes. As you can see from this figure, The highest contribution on the compression can come from the source and the destination address, since each address consists of 128 bits or 8 bytes. So the first field of the IPv6 header format represents the version. So it consists of 4 bits and it represents the IP version number. So for the IP version 6, the sequence of bits usually is defined to be 0110. Now, the next field is the traffic class of 8 bits. Now, the bits of this field represents 2 values. The 6th most significant bits hold the what is called differentiated services or diffserv or DS field. So diffserv is used by the network for traffic management and classification and for providing quality of service. Now, the default value, 6 zeros in row, corresponds to the classic service known as the best effort. The last 2 bits of the field are used for explicit congestion notification, ECN, and it allows for end-to-end notification of network congestion. Next, we have the flow label field, which is a 20-bit field, and it is used as an identifier by a source node to label the IPv6 packet that belong to the same flow. For example, a voice over IP application or a TCP session, to request spatial treatment by the intermediate IPv6 routers or nodes. The special flow label 0 means that packet does not belong to any flow. Next, we have the payload length, which consists of 16 bits, and it indicates the size of the payload in bytes, in octet. Then we have the next header field. This is 8-bit field, identifies the next protocol header following the IPv6 header, or in other words, the transport layer protocol. Then we have 8-bit hop limit field, which replaces the time to live field in IPv4. So this field represents the maximum number of routers the IPv6 packet can pass through. So basically, this value is decremented by 1 at each forwarding node, and the packet is discarded if it becomes 0. The next field is the source address, which consists of 128 bits, and it is the field of the original source of the IPv6 datagram. And finally, we have the same thing for the destination address. So we have 128 bits address field of the destination of the IPv6 datagram. So this was a quick overview about the IPv6 addressing and the header format, which will help us to go over the 6LoWPAN adaptation layer and more specifically to the section 3 regarding the IPv6 header compression. Now, I will proceed with the 6LoWPAN adaptation layer. I will give you an overview. So basically what we have is a new adaptation layer. If you think about the OZ or TCP/IP stack, or the stack that I showed you in the very beginning of my talk, and it lies between the IP layer and the MAC layer. So we have this adaptation layer. So the idea is that the 6LoWPAN adaptation layer will be in charge for transporting IPv6 packets over the what is called IEEE 802.15.4 radio links, or can be even wired if we're talking about power line communication in smart grid networks. And this adaptation layer comes with a series of mechanisms or operations. So the first one is called the compression, and the objective is to reduce the IPv6 and UDP headers down to a few bytes. Next, we have the compression operation. where the objective is to split the large IPv6 datagram into smaller fragments if the compression mechanism is not sufficient. Then we have the fragment delivery mechanisms that allows fragment forwarding in a multi-hop network. So actually, the RFC 4944 defines two modes that are called the mesh under and route over. Now, with mesh under, the operation of fragment forwarding takes place at the 6LoWPAN adaptation layer based on the layer 2 MAC addresses. While the route over mode, the operation takes place at the layer 3 based on the IP. Now, furthermore, recently we have two standards that are defined in the end of 2020. So the first is related to what's called 6LoWPAN fragment forwarding, 6LFF, and it is an alternate approach where an intermediate node will forward the fragments without proceeding with a reassembly of the complete IPv6 datagram first. So we don't need to do the reassembly and then the fragmentation of the IPv6 packets before forwarding to the next hop. So here, each fragment that is received, it will be directly forwarded to the next hop. So that's the concept of 6LFF and it is defined at the RFC 8930. While the latest standard, the 6LoWPAN selective fragment recovery mechanism, RFC 4931, it is in charge to recovery of the missing fragments. So basically, it proposes a recovery mechanism for potential lost fragments between the 6LoWPAN endpoints, as well as a minimal flow control to prevent bloat in the mesh network. So that's it. So what I'm proposing to you today is, for the remaining time, I will focus on the first operation, on the first mechanism, which is the header compression, which is defined in RFC 6282. And if time permits, I will proceed with the fragmentation. But the main, the core of this talk will be the compression part. Now, I will proceed with the problem statement in this slide. So basically what we have the IEEE standard, the 802.15.4, which comes with a very small, what it's called MTU, maximum transmission unit, of 127 bytes. Okay. Now, considering that an IPv6 header consists of 40 bytes by default, and UDP header of 8 bytes, while the IEEE 802.15.4 MAC header can be up to 25 bytes if there is no security employed, or 46 bytes if we have a security, if the security field is used. So as a result, there are either 54 bytes left for the payload when security is not considered, or 33 bytes when the security is considered. Now, the problem is that the IPv6 requires links to support an MTU, maximum transmission unit, of 1208 bytes. Okay, so therefore it is not possible to transmit IPv6 packets over 802.15.4 technology as it is. So therefore, header compression and potentially link layer fragmentation and reassembly operations are required. So this is the problem that we are going to solve, or we're going to see how it is solved by the IETF community. Now, 6LoWPAN, the adaptation layer, employs what is called header staking and defines encapsulation formats that are self-contained headers to separate orthogonal concepts and keep the headers small and easy to parse. Now, each header expresses a specific capability, such as the fragmentation, which is the one in blue here, or the compression, which is the green part here, so IP header compression. Moreover, in order to identify by 6LoWPAN, each header contains a header type field placed at the beginning of each header. So this is the dispatch that you see in the beginning each time. Okay, frag type, frag or fragmentation type, or IPHC dispatch. So this is the link for my next slide, where we are going to see all of these dispatch types. So basically, RFC 4944 comes with dispatch codes to identify the header fields that follow. So including uncompressed IPv6, which is the one here that starts with 01, series of 0 and then 1. So we have a packet or IPv6, an uncompressed IPv6 address. Or when we have a compressed header, IPv6 header. So here the dispatch should start with 011. So this indicates that we have a compressed IPv6. Then we have two dispatch types for the header fragmentation. So 11 and 3 zeros, this is for the first header, and for the subsequent fragments, we have 11100. And here in this figure, the whole process of fragmentation and compression of an IPv6 datagram is illustrated. So this is an overview. So basically, what we have here is an IPv6 datagram. So as you can see here, we have a large packet. And the idea is that the source node it tends to send this packet to the destination, but because we do have this problem of 127 bytes MTU at the layer 2, so what happens is that the source node should compress the IPv6 header, so which is this one here. As you can see, the dispatch type 011, which represents that we do have a compressed IPv6 plus the IPv6, the compressed fields. So this is the compressed for the IPv6. Then if there are IPv6 header fields that cannot be compressed, as we are going to see later in details, these fields must carry inline. Similarly, we do have the same process for the next header compression, and more specifically for the UDP header. And in the very beginning, as you can see here, we do have what it's called the frag1. So it represents that we do have a fragmentation of an IPv6 datagram. And this is the first fragment because it starts with 11 and 3 zeros. So 11, 3 zeros represents that I have, this is my first fragment of an IPv6 datagram. 011 represents that this is a compressed IPv6. And then later, as we will see, there is another dispatch type that represents the next header compression. We are going to see this in detail. So then, as you can see, we have the first part of the payload. Then we do have similarly for the second part. And finally, the last part of the IPv6 datagram is carried through the third fragment. Now, in this third section, I will try to give the whole details of how we are going to compress field by field the original IPv6 header to what's called compressed header. Now, as you can see here, the main goal of 6LoWPAN compression mechanism is to take the original IPv6 header, so these 40 bytes here, and add a few bits which indicates how the original IPv6 header is actually compressed. So here we have the additional bits. So these additional bits actually that are added form what is called the compressed header or the IPv6 header compression, IPHC. I think that's it. And the objective of this operation, of this procedure, is that the receiver of the compressed packet, by adding these fields of the compressed header, can at the end decompress and obtain the original IPv6 packet. Now, the header compression principle is elementary, meaning any field that can be guessed by the destination endpoint is not actually sent. Indeed, some of the header fields can be elided, meaning won't be transmitted for different reasons, as we will see here. So first, we have the version. So actually, the version field can be elided in all cases, since only IPv6 is employed. So we have only the IP version 6 that's employed, and therefore we don't need to send this information, because the receiver expects that the packet that it will receive comes with IP version 6. The second case is the payload length. Indeed, this field can be elided as well, since it can be inferred from the lower layers, for example, from the 6LoWPAN fragmentation header, or from the IEEE 802.15.4 MAC header, so from the layer 2. So as a result, these two fields that are in yellow are not necessary actually to send to the destination. The destination may either retrieve from the layer 2, which is the payload length, or the version. This is it's an information that it is aware of. Now this is the complicated part, so I'm going step by step, so please don't be shocked. So the 6LoWPAN IP header compression, so IPHC, encoding consists of 2 bytes, okay, 16 bits, and it may be extended by another byte to support additional context encoding. So the methodology is actually quite simple, and indeed the idea is to have compressed header fields which match the fields in the original IPv6 header. Okay, so basically in the figure here below in the bottom, you see the IPHC, so the IPv6 header compression encoding. As you can see, first we have the 3 bits that which is the dispatch value, and the value indicates that the nature of the 6LoWPAN frame, and in this case is 011, and this represents that we have a compressed IPv6 diagram. Now here we got now in the following fields we are going to see step by step all the fields, and to understand how the compression process takes place. So first, as you can see, we have the what's called TF. So TF field handles the compression of the traffic class and flow label fields of the original IPv6 header, so the one that I showed you in the very beginning of this presentation. Now, considering that it is, as you can see here, 2-bit field, it means that there are 4 combinations of these 2 bits. So basically, it means that if it is 0 or 00, then all information will be carried in line. If it is 01, then we will have only ECM plus the flow label. If it is 10, then we have only the ECM and the differentiated service. And finally, if it is 11, it means we have nothing to transmit, so we have quite efficient compression mechanism. So next field is the next header field, which refers to the next header of the original IPv6, and it indicates whether the next header field is not compressed. Excuse me. It indicates whether the next header field is compressed or not. Okay, so for example, if we have a UDP protocol, whether the UDP protocol is compressed or not, as simple as that. Then we have the HLIM, which stands for hop limit, and it represents actually the hop limit of the original IPv6. And as you can see here, there are 4 well-known values. So we have either 255, either 64, or 1, or 0. So basically, the 00 bits represents that the value of the hop limit is something not among the 164 or 255, so it must be carried in line. So the transmitter must transmit this information. Now, if we have the bits equal to 01, then it means that the receiver will understand that the hop limit is equal to 1. If it is 10, the receiver will decode and will understand that the hop limit is the value of the hop limit equals to 64, and respectively we have the final value, which is equal to 255. Okay, so once again we have a compression efficiency if and only if the transmitter is using either 1, 64, or 255 values. If not, then we have 00, and this information must be carried in line. Next, we have what is called the CID field, which stands for Context Identifier Extension. It adds a context to allows 16 source and destination prefixes by default. So if the CID, Context Identifier Extension, is equal to 1, then it means that we do have a context. So basically it means that the transmitter and the receiver, they have agreed on a specific context, on a specific prefix, and there will be additional 8 bits after the DAM. So as you can see my pointer here, after DAM we do have 8 bits additionally that will identify which is the prefix of the source and the destination. So that's why we have 8, because we need 4 bits for the source to represent the prefix and 4 bits of the destination of the prefix of the destination. So that's why we have 8 bits in total. So 2 power of 4, we have 16 different contexts. Next, we have what's called the SAC and the SAM. So SAC and this SAC represents the source address compression, and it indicates whether we have a stateless or context-based address. So if it is 0, it means that we do not use context. If it is 1, it means that we do have a context-based. So similarly for the DAC, so this is for destination address compression, and it represents exactly the same whether or not we are using the context or if we have a stateless approach. Next, we have SAM and DAM, and SAM and DAM fields represent the source and destination address mode, and depending on the combination, we might have different byte sizes. So it highly depends on whether the addresses are link local or global. And finally, there is the field M, so which stands for multicast compression. It indicates whether the destination address is a multicast address or not. So this is the whole concept of IP header compression encoding system. And now I will give you 2 examples, and I hope that with these examples things will be much more clear. Of course, if you have questions, I can answer right after. So the first example is a link local multicast, and here on the left side you can see the original IPv6 link local multicast address, while on the right side you have the compressed header, okay, which starts with which starts with 2 bytes. So we have 16 bits here, where the first 3 are 0, 1, 1, which represents that we have a compressed IPv6 address. Now we are going to analyze field by field the original IPv6 header and to check what can be aligned or compressed and what must be carried in line. So the first field, as I told you in the very beginning, is the version. So it's the version field, IPv6. Then the second field here is the traffic class, okay, which consists once again of 8 bits, and it represents two values. We have the differentiated service and the explicit congestion notification, so ECN. Then we have the 20-bit flow label field, which is used as an identifier by a source node to label the IPv6 packet that belong to the same flow. Then we have a 16-bit field, which represents the payload length. Then we have the next header. So we have the field of next header field, which identifies the next protocol header following the IPv6 header, such as ICMP, UDP, TCP. Now, if you're wondering which protocol the value 3A represents in a 3A in a hexadecimal format, you may easily find it if you go and search on Google by typing something like next header IPv6 values. So you will have like a list of results. Or if you go directly to IANA, and there you will find this value of 58. So 58 is the decimal version of the hexadecimal 3A, and you will realize that in this specific example, the next header is the ICMPv6. Now, the next field here is the hop limit, which consists of 8 bits. Then we have two fields that are the source and destination addresses of the IPv6 datagram, where each consists of 128 bits. So here is the source, and here below is the destination address. And finally, the remaining part represents the payload, the actual payload. Now, let's see the compressed header. So as you can see, first is the dispatch. So we have the 011, which represents that we have a compressed IPv6 datagram. Now, analyzing field by field, the header of the original IPv6. First, we have the version field, so the yellow part here. And as I said earlier, the version field can be elided in all cases, since only IPv6 is employed. And therefore, the value of this field is always 6. So we don't need to take any action for this field. Then we have the field of the compressed header, the TF. And in this case, in this example, it is labeled as 10. And therefore, only the flow label is elided, and the rest is carried in line. As you can see here, E0 is carried in line, because we cannot, it is not compressed, so we have to provide this information to the destination as it is. So next, next we have the payload length field, which can be as well elided like the version, since it can be inferred from the lower layers, either from the 6LoWPAN fragmentation header or from the layer 2 802.15.4 header. So then we have the 1-bit field, the next header field. In this example, it is labeled as 0, since next header field is not compressed, and thus all 8 bits for next header are carried in line. So as you can see here, 3A of the which represents the ICMPv6 must be carried in line. So right after the compressed header, we do have the IPv6 header fields that are carried in line. So the next field is the hop limit. So this is the value here. We have FF. So if we go to a converter and we have a look and we will realize that FF in hexadecimal is 255 in decimal, so which is good news for us. Therefore, this field can be compressed, and to compress 255, we have the 2 bits 1 and 1. So the next fields are the context identifier extension, which is labeled to 0, as you can see here, to indicate that no additional CID field is employed. Okay, so we don't have any shared context between the two nodes, between the two endpoint nodes. While the stack field is also labeled 0, so this one here, to indicate that a stateless approach is employed for the compression of the source address, which means basically that a link local prefix is used. How do we know that? If we go to in the beginning of the IPv6 address, FE80, so this is a typical link local prefix. So based on this information, we know that we have a link local, so we can indicate the SAC value as 0. Next, we have the sum field, which is equal to 11. And what does it mean, 11? It means that we have the best case scenario in terms of compression efficiency. So basically, it indicates that all 128 bits of the source IPv6 address can be elided. So as you can see here, all this blue part, the first blue block, can be elided. Indeed, we have the prefix. So the prefix means the first 64 bits of the IPv6 address is link local. Okay, so this is why we have SAC equal to 0. While the interface ID, the remaining 64 bits, is formed from the layer 2 source address. So here you can see this is another point where we can retrieve some information. So this is typical approach to retrieve or to create an IPv6 address based on the MAC address. So that's why you see here FFFE in the interface ID part. So it represents that we have formed an IPv6 address based on the MAC address. So we do have a link local address, IPv6 source address here. So this is for the sum field. Next, we have the multicast compression, the M field, which is equal to 1. So 1, what does it mean? It means that we have a destination address, which is a multicast address. It is true. Why? Because as you can see here, FF02, it is a typical multicast address. Okay, so that's why we have M equal to 1. And then we have DAC equal to 0, which is which represents a stateless approach as well for the compression of the destination address. Indeed, here we have as well a link local scope, so the DAC is equal to 0. Finally, we have the DAM field, which is equal to 1 and 1. So since we have a multicast address, which has the format of FF02 and then series of 0 and then 2 values, XX. So XX here is the 0, 1. So this specific format of FF02 and then series of 0 and XX, it is defined by the RFC 6282 to represent that we have the DAM is equal to 1, 1. And what does it mean? It means that only the last 8 bits are carried in line. And this is why you see here 0, 1 at the end. So which indicates that we can elide almost the whole address except the last 8 bits. So the last 8 bits must be transmitted in line. I think that's it in terms of the compressed header. And now let's see the results. So what we have here is 6LoWPAN compression mechanism where we have achieved to compress the 40 bytes of the original IPv6 address down to 5 bytes. So which indicates quite good efficiency level. So more specifically, what we have 2 bytes because of the header, of the compressed header. So this is, we're always going to have these 2 bytes. So this one we cannot avoid. Plus the 3 bytes because we have three IPv6 header fields that are carried in line. Okay. So 2 plus 3, we have in total 5 bytes. Not too bad. For I mean, from compressing from 40 bytes down to 5 bytes. Now I will quickly show you another example, which is a global unicast, to see the other side of the coin. So here I'm skipping all the details and I'm going directly to the results. So here we have done the compression for the compressed header. So as you can see here, we have a TCP at the transport layer. Now the idea here, I mean, not the idea, but the problem here actually are the source and destination addresses. So both of them are global. So when they are global, it means that we have bad news, and the bad news is that we cannot compress them. So that's why SAM and DAM, they are 0, 0, 0, 0, and DAC are 1, 1. So which means that we will have to send completely the source and destination addresses actually in line. Okay, so which makes it in total 32 bytes, 16 plus 16 bytes, and then we have 1 byte to transmit the information regarding the next header field. So this 06, the TCP value, and plus we have, as I said, by default the 2 bytes for the compressed header. So in total we have 32 bytes, 35, excuse me. So as you can see here, as a result, 6LoWPAN compression mechanism is not that efficient when global addresses are employed without, be careful, considering what is called common context among the nodes. So when CID is not employed, so we do not have well-known prefixes between the nodes, then the compression efficiency is not so high, it's not so big. That's it. So Nalini, if I have 3 to 5 minutes, I could continue with the UDP header compression. I have very few slides, and then I am happy to.
Yes, no, please go ahead.
Thank you. The last section here is dedicated for the UDP header compression. So basically, this is the typical UDP header format. So in case you are not aware, so I mean, in this slide we have everything. So we have the source port, the destination port, the length, and the checksum. So first we have the source port, which is a field that identifies the port of the transmitter. Then we have the destination port that identifies the port of the receiver. The third field is the length, which specifies the length in bytes of the UDP header and data. And finally, we have the checksum field for error checking of the UDP header and data. Okay. Now, in RFC 6282, a specific range of UDP port numbers is defined. So basically, it allows for the source and for the destination ports to be compressed from 16 bits down to 4 bits. Okay, so as you can see here, we have 16 bits for the source address, for the source port, and 16 bits for the destination port. Now, the idea is that if the 6LoWPAN network will use the UDP ports that are within this this pool of ports from 16 to 32, then these ports can be compressed up to 4 bits. As simple as that. Next, regarding the UDP length field, it can be as well elided, similar to IPv6 payload length, since it can be inferred from the lower layers. And finally, we have the checksum field, which will be either carried inline if we are using, be careful, RFC 4944, or it can be elided if we are using the RFC 6282. Indeed, with RFC 6282, a compressor in the source transport endpoint may elide the UDP checksum if it is authorized by the upper layer. Okay. Now, in the figure here, the UDP header encoding format, which consists of 8 bits, is illustrated. So we have, according to RFC 6282, the first 5 bits, which is the dispatch value. If you remember the 011 for the IPv6, here we have 11110, and it indicates that we have UDP header compression. Basically, with this dispatch value, we know that there is a compressed UDP protocol. As simple as that. Then the next field is the C, which represents the checksum. And as simple as that, when it is 0, this field is not compressed, and vice versa. When it is equal to 1, it is elided. Okay. Finally, we have the 2-bit field, which represents the ports, where 0 indicates that there is no compression, so all the information must be carried inline. 01 indicates that only the first 8 bits of the destination port is elided. The 10 indicates that the first 8 bits from the source port is elided. And finally, most efficient combination is the 11, which represents that the first 12 bits from both source and destination ports are elided, and thus only the remaining 4 bits are sent. So I would like to once again to show you this figure, where you can see again all the fields for the fragmentation part, which unfortunately I didn't have the time to show you in details. I hope I will have the opportunity in the future. For the fragmentation, for the first fragment, frag1, and frag_n represents the subsequent fragments. To summarize, 011 represents the compression of the IPv6, of the compressed IPv6 packet, and 11110, the one that we saw earlier, represents that we have a compressed UDP header. Okay, and then if we have a dedicated space for the inline next header fields, both for the IP and for the UDP. That was my presentation.